what can we predict about francium? So that's too vague. Given the above information, which of the following is a reasonable density for potassium? Okay, as written, that's a horrible question. Why? I don't expect you to give me an exact number, okay, for any kind of question like this. What I expect you to do is to be able to interpret the data and give me a reasonable guess at that number. Okay, so if we were just given this, okay, what we would do is go back up to our table and say, where is potassium found? Well, thankfully I blocked that all out so we can't see it. Where is potassium according to our periodic table? Underneath sodium and above rubidium. So if we take a look at the density for lithium to sodium, what happens to the density? It goes up. What happens as we move from sodium to rubidium? Goes up. So it apparently continues to go up. So a reasonable guess for our potassium would be a number that is bigger than, so we take our guess and just say it's X. It's got to be bigger than, where's my bigger than sign? There it is. Bigger than 0.97. So let's call it 50,000. Is that a reasonable guess? That's bigger than 0.97, right? No. Why is that unreasonable? We've got another bound. Let's look at the other direction. Cesium to rubidium, what happens to the density? It goes down. Rubidium to sodium. Okay, so if we look in the reverse trend, our densities go down. That means our potassium should be less than that for the rubidium. So we would take a look at our multiple choice answers and guess somewhere in between those two. Okay, not higher or lower than that. Yes, the multiple choice answers would separate accordingly. I'm not going to give you two multiple choice answers that sit directly between those two values. Okay? That's a bit rude. Okay? And I try to not be rude. Try. Sometimes I fail. Okay? So if we looked at multiple choice answers, we can now say, okay, which of those makes the most sense? B, 1.23. Okay, it is a value somewhere in between there. Okay, which now brings up our next question. Are we right? No. Does that matter? No. It's about interpreting the data given to you. Regardless of whether or not your interpretation matched reality, okay, is irrelevant. What you need to be able to do is interpret the information given and apply those rules accordingly. Okay? Make sense? Okay. Chemical properties. So just like our physical properties match within an individual family, okay, we also see chemical properties matching as well. So if we take a look at the alkali metals, they all have oxides of this general formula. We take two metals to one oxygen. So lithium oxides are two lithiums, one oxygen. Sodium, two sodiums, one oxygen. Okay, so everything within that column is the same formula. So in an exam, I could ask the formula, or state the formula for a chloride of calcium is CaCl2. What is the formula for the chloride of barium? So first thing we could come up with would be, what is the symbol for barium? Our symbol for barium is Ba. Where does that show up on the periodic table? Which column? The second column. Where does calcium show up? Second column. They're part of the same family. Okay, which means their chemistry is also the same. So what formula do we expect out of this? BaCl2. There's your answer. New question. What is the formula for the chloride of chromium? What's the symbol for chromium? Where is chromium with respect to barium? Or, sorry, calcium. It's a transition metal versus, what are those, the alkaline earth metal? Okay, so let's throw down some multiple choice answers. We're going to go CrCl, CrCl2, CrCl4. Actually, let me change that up. No, I'm going to leave it at that. Or impossible to tell. Answer A, B, C, D. What's your answer? What a sneaky little twerp. Possible to tell. You don't have the ability to do that interpretation based on the information given to you. Chromium and calcium are not in the same family. We don't know any parallels that would connect those two. Okay. Maybe you know a wicked lot about chromium and you might be able to predict what the actual formula was, which is why I danced around CrCl4 versus another potential compound. Okay. So I would try and pick things that definitely don't form. Right? Is that tricky? Yes. But you have to understand why you're making these parallels. Follow the results given to you and interpret them accordingly. If you're given mismatched data, oh well, you can't do anything with it. Right? Say you can't do anything with it. Make sense? Okay. Oh, I forgot about that. So there's a quiz. Tried to make it relatively straightforward. Went through and set it up where you're just going to try and tell me what type of compound. So you're almost looking at multiple choice at that point for the type of compound. And then try and give me two names. So that gives you 5, 6, 7 answers on here. Give me 5 correct answers. I'll give you full credit. Extras are missing. We can go through it in office hours if you like. All right, or online. Chapter 4. So now we're jumping back to Chapter 4, and we're going to jump through the initial sections on what is light. Okay, this is something that I want you to read up on, but it's not a huge issue as far as lecturing goes. Light has a wave nature associated with it, which means when we look at a wave, we can break it down into individual components. We can look at the frequency, and we can look at the wavelength. Your wavelength measures the distance between your peaks. So here to here is your wavelength, which carries the symbol lambda. And your frequency looks at an arbitrary distance. Within that arbitrary distance, how many peaks showed up. So if we compare these, the second one or the bottom one has a higher frequency because more peaks showed up within that arbitrary distance. Okay? So the frequency is how many do we get per an individual cycle, and the other case is how broad those individual wavelengths are. Okay, there is a number associated with light. We're looking at the speed of light being 3 times 10 to the 8th meters per second. We thankfully don't really do any calculations involving wavelength, frequency, or even really the speed of light, so don't stress too much on that. If you move into 151, you will run calculations with it, so it's not a bad idea if you want to ask about that to play around with it. The other thing we can look at is the energy associated with these individual lights. Okay, so what we're used to seeing is just the visible spectrum of the electromagnetic radiation spectrum. Okay, so visible light is a small section of energy within the entire continuous spectrum, or our radiant energy spectrum. Okay? So you should be able to pick up some information out of that based on energy. So we can look at wavelength, we can look at frequency, and both of those can be compiled together to produce an energy associated with an individual color of light. So as far as that interpretation goes, we could look at both the colors and we could look at all of the individual types of radiant energy that come off of it. So we got a nice little graph here that kind of sets this up for us, okay, or at least measures everything out so we can see them. But we don't really see, oh, it does say energy on it. All right, so let's go through and take a look for our first question. Which color has the highest energy, red, green, blue, or yellow? Okay. I tended to hate this question at first because I could never quite remember why. Okay. Then I thought of an interesting little phenomenon. Okay. When we go outside, what are we afraid of? What do we try and protect ourselves from? Ultraviolet radiation coming from the sun. Okay. Why are we trying to protect ourselves from that? Really high energy. Okay. We kind of avoid the heat, okay, or our infrared energy, which is ultimately just a measure of heat. We try to avoid that. We don't go out in the heat as often, okay? But we aren't really concerned about that. The UV radiation we are concerned about. We put on skin block. We put on things to protect ourselves from that ultraviolet radiation, okay? Ultraviolet. Violet means what color? Purple. So when we look at our color spectrum, okay, ultraviolet we're concerned about being our highest energy. Where is violet closest to? The purple end of our spectrum, or the red end of our spectrum? Purple end. Ultraviolet is our higher energy particle. Purple is our higher energy visible light. Red, being on the complete opposite end of the spectrum, is the lowest energy. Okay, how can you decide the order of those individual colors that go into it? Because very rarely do you actually see a spectrum given to you like this. Anybody know that famous guy's name? I don't have yellow. G. Don't have indigo. Mr. Roy G. Biv. Right. Roy G. Biv sets us up with the color pattern within that. Red, orange, yellow, green, blue, indigo, violet. Okay. That organizes at least the colors relative to each other. If you're asked a question like this, you can remember, well, ultraviolet is our high energy. Why is my pen not writing? High energy. And our opposite end of our high energy would be low energy. We now have a way of going through and specifying with our question, where do our individual colors show up with respect to the energies? Okay? So that can help with the color type questions. That is pretty much the extent of those color questions. There's an awful lot of other radiative emissions that can go in there. You've got radio, TV, microwaves, infrared, ultraviolet, X-rays, gamma rays, and cosmic rays. All of those are different forms of radiant energy. Okay? As far as deciding which of those has the highest energy, that becomes a little bit trickier because you'd need to know how all of those stack out against each other. Okay? That is something I would ask you in the homework, not something I would ask you on an exam, because that would assume that you had all of those memorized, and I don't have the order of them memorized. Okay? So if I can't do it, I don't expect you to do it.
What is there gaps between
There are, sorry, what do you mean? Try that again?
yeah, like the cosmic gamma and X-ray?
Why is there a large gap between gamma and X-rays?
A little gap and then violet.
Within this spectrum, it is a continuous spectrum, full thing. Okay? The energy does not really change or subtly changes as we move up and through it. So where is the difference between our visible and ultraviolet? That is something we arbitrarily decided, and that arbitrary basis was based on, oh, come on, what we see. If we can't see that light, then we would call that ultraviolet energy as opposed to the visible energy spectrum. If we looked at the difference between our visible spectrum and the infrared side, where is that cutoff? So again, that cutoff is what we see. Okay? Different people can see better at each of those ends of the spectrum. There are some people that can see down to 400. Most people start to lose their vision about 410 nanometers. Okay? So you can't actually see, or most people don't see that end of the spectrum. Same kind of thing happens out at the other end. Okay? Depending on the person's eyesight, they may actually be able to pick up a little bit further or a little bit lower wavelength, okay, or higher energy, and that all just depends on the biological person. When we go through and look at the other individual cutoffs, we've just kind of established these random cutoffs, much like chemical versus physical changes. It's a complete spectrum across it, and we arbitrarily decided roughly in between is where they're cut off from each other. Okay? Same thing is happening here. Okay, so they're kind of an arbitrary cutoff in between those. We can't really say one way or another for the difference between your gamma versus X-rays. See a larger gap there, probably because gamma rays have a higher energy and X-rays don't quite clear that energy gap. Okay, so each of those are fuzzy in between. What we really want to get into is this process known as the emission line spectrum, okay, or just a line spectrum, also known as an atomic line spectrum. Okay, and what's happening in this case is that we're taking a sample of gas, okay, and that gas is one of our elements. In this case, hydrogen. Good. Okay, I did remember that. We're looking at hydrogen in a sealed tube, so it just has hydrogen in it. And just like we did with the cathode ray and we tried to figure out the existence of electrons, we're going to pump a bunch of electric current into this tube. Those electrons are going to jump from one side of the tube to the other. But as they jump, what do they run into? Hydrogen. Okay? Well, now hydrogen gets hit by this electron and it makes an excited state hydrogen. That excited state hydrogen is what's contributing to these colors. So our excited state hydrogen excites an electron to a higher energy within its system. When that energy, or when that electron relaxes back down to its ground state, to its stable state, it emits light. That light is what we're seeing within the atomic line spectrum. Okay, kind of makes sense? So we just take an electron from stable state, make it really excited. When it relaxes back, it emits that light.
Would different gases let off different colors of light?
That's a good question. And yes, it is true. Okay? So different gases do give off different colors of light, and it's going to come back to why. Okay? If we look at our model of the atom, we said we had our nucleus with our protons and our neutrons all densely packed in our center, and then the electrons were just on the outside. Did we say where on the outside? No, we just said they're somewhere on the outside. We don't really care. Okay? Which means if we take those electrons and move them around, okay, our nucleus, they're going to start to move to different energy states. The closer it is to the nucleus, the more the charges balance out. Okay? The further it is from the nucleus, the less the charges balance out. So the further we get from the nucleus, the higher energy the electron becomes because it's now more negative. The closer it gets to the nucleus, it's starting to be canceled out by our nucleus. That charge is canceled out. We're at a lower energy state because we're not charged. Okay? If we don't have defined places for where our electrons exist in an atom, what ends up happening? Well, that means when I fire energy into it, I can excite any one of those electrons to an excited state that when it comes back down, emits light. Okay? Because my electrons are now all at a whole spectrum of different energy states, I would expect when I look at the spectrum of light, the atomic line spectrum, that I should see all the colors representing all of the different energy states. Do we see that? No. We see very distinct color bands. Okay, what does that mean? That means our electrons can only move from distinct energy states. Okay, they don't exist everywhere in the nucleus or in our atom. They're only in very specific places. Because when I pick it up and move it to another specific place, the difference in energy there is going to correlate to the light emitted. Okay? And because I only see one of those colors, or for instance 3 of those colors here, there's only 3 possible energy states that those electrons can exist in. Okay? Outside of that, I'm done. There is no other option. I don't get a full color spectrum. Okay? This is a really, really important discovery. What we're now saying is that our electrons are not in a free-flowing soup around our nucleus. They exist in distinct homes, okay, or orbitals, or energy levels. It's because of this that we now run into the Bohr model of the atom. Right? And what that's saying, I see it, give me a sec. What that's saying is that when we look at our electrons can potentially jump between those orbital energies, but they can't jump halfway. Okay? If I look at the energy gap, say between that first one and that second one, let's say this is 6 kilojoules of energy. If I give my electron at that lower energy level 5 kilojoules of energy, can it make it to that next energy level? No. So what happens? Nothing. It stays in that lower energy state. It has nowhere else to go. What if I give it 7 kilojoules of energy? It jumps up to the next one. Okay? And that extra kilojoule of energy, let's say, isn't enough to make the next bridge. So what ends up happening is our electron jumps up to that 6th or 2nd energy state, and it stays there as an excited state. When it relaxes back down to the ground state, it releases that 6 kilojoules of energy as light. There's our line spectrum. Okay? So Bohr's model says our electrons exist in these definite orbitals. Okay? They're quantized, meaning they're numerically ordered. We don't have a spectrum. Back to your question.
I was just going to ask, if you had a larger gas, would there be more than 3 colors? Would you have more than 3 orbitals?
You can pick up different, and it's not as simple as how many orbitals there are. But you got the right idea. Yes, as we get larger and larger, we can start putting electrons in different energy levels, and we can start seeing different colors come out of it.
So you'd see more than 3 colors, though?
Yes.
I found in the book somewhere, I can't find it now, but with neon, we think, oh, it must be neon in the tube that makes it a certain color, but neon is only like pinkish red, but if you see neon in green or yellow, there are other
Careful. Yes and no. What you're swapping is our phenomenon known as neon tubes. Neon tubes are not neon. Okay? What neon tubes are is a various mixture of different gases to give a particular color that we want. So it's the same process as we just looked at on this previous slide here. We take our tube, we remove almost everything in it, and we put a gas into it. If I want a green color, neon doesn't work. Okay? If I want, I forget what neon is, a reddish color, then neon works. That's the gas that's in there. We call all of those tubes, for the sake of simplicity, neon tubes, even though they aren't actually neon that's in them. Okay? So this concept is what's known as the quantum concept. Let's try that again. Massive amount of mathematics behind it. Okay? Stupidly impressive to watch someone go through and solve the quantum mechanics and the physics behind it. I'm not even going to attempt to try that because it's that beautiful and I would ruin it horribly. Okay? What we're looking at is the difference in this situation is this idea of a quantized state versus a continuous state. And the example that your book gives, which is a pretty good one, is steps versus a ramp. Okay? When we look at the ramp, the ball can roll freely down that. It can exist at every single energy along that slope. When we look at steps, our ball can only have particular energies where it hits the individual step. We can't have the energy in between steps because it never exists at that point. It's only moving between the other points. Kind of makes sense? So what we're concerned about is this quantized versus continuous application. Really want to talk more, but I can't. Okay? So we'll talk more about this on Thursday. We probably won't get into the nomenclature activity because we spent so much time on it today.